the second section of chapter 11. So we will talk about half-range expansion. Right. So we will consider a function f, okay, defined in the interval from 0 to L. And this function satisfies the required conditions in theorem 11.1.2, which is just the Fourier series extension theorem, but over the interval. Because in that theorem, the condition is required over the interval from minus I to pi 1. But here, it's just over the interval. For example, the function should be absolutely integrable over this interval from 0 to L. Right? The second thing is that the function should have left hand and right hand limits at every point in this interval. The third thing is that this function should have left hand derivatives and the right hand derivatives at every point in this interval. Right? So we have three conditions. And so we assume that such a function, even though it is defined only on this interval, but the three required conditions in this theorem are satisfied by this function. All right. So an example of this, we may say like here, from 0 to L, for example. And this is maybe called 1. And so at L, we can select, for example, you can select that the value defined is 0. Okay? It's up to you. So it's just an example, a very simple example here. Okay? A very simple example. Now, our purpose is that we want to represent f as over x as the sum of a trigonal metric Fourier series. Okay, so we want to represent the sum. By extending f into a periodic function. Right, so our purpose is that because the function defined only on this finite interval, right? But to be able to represent a function by a trigonometric Fourier series, well, actually we have to extend f to be a periodic function. Okay, and so if we do so by regarding f of x, x is in 0 to L, as, okay, so if we do this way, as in the period of a periodic function, we say f star, okay, is period, yeah, i.e. So this is f star x, and this one is f of x. So f of x is just in a period of this periodic function, and this periodic function f star has period f. Okay, so this one. So you can regard it. All right, and because f star is a periodic function and satisfy theorem 11.1.2. Okay, because f satisfies the condition. Okay. Oh, I forgot to say that it is piecewise continuous. Okay, not just. Alright, so let me repeat it. Okay, exactly. What I mentioned actually is just a consequence of the condition mentioned in theorem 11.1.2. So maybe I stated it again. Okay, so what do we mean? The required conditions is that this function is piecewise continuous. Okay, so let me see. Here, 1, f is piecewise. Continuous. L. Okay. The second thing is that f has the left hand and right hand derivatives. Okay. At each point in 0 to L. So these two functions, these two conditions. And I think you already, because is that in the first quiz, I asked you to verify that each function that especially quiz number 2 and 3 for each periodic function, you have to verify that which is piecewise continuous from minus pi to pi, and each of the function in either problem has the left hand and the right hand derivatives. Because both functions are simple functions, I think it's quite easy for you to verify. And here, I just assume that this particular function here satisfies these two conditions. So, so that you get the idea you have that. But one, if you are very careful, you may notice that what if we define the value of the function f at L to be, say, here, instead of here. Suppose that. Suppose I change my mind. Okay. Now for that, then you have contradiction. Because that at this particular point, at the 0, right? At 0 here, you have when x equals to 0, f of 0 is 0, so it's fine. But if we regard f star to be periodic, now you have conflict because that FL, because in this case, F0 is not equal to FL. Okay? But for periodic function, if we regard, so we require that f star 0 should be equal to f star L, right? For a periodic function, right? And so you have a conflict just at one single point here, but that's fine. That's fine, okay? Because that except possible points here, one point here, but that you still that these two functions. So the f function essentially you can say that the f function is in a period of the periodic function for almost everywhere. You can say so. But for here, actually, it's set just one point. So we will see that. But so that is if you are careful, you can see that. So but we will not use that. The reason is that then the Fourier series and the trigonometric Fourier series expansion of f and x would have a0, a1, b1, a2, b2, etc. as coefficient. And it contains both cosine and the sine terms. In general, so in general, you will have cosine and sine terms. Okay, this is general relation. But we can simplify the trigonometric Fourier series expansion by using an even periodic extension we say Fe of F, or second odd periodic extension of F. Okay. As follows. Right. So we have alternative choices. Right. If we okay, you can insist to regard f of x as in a period, one period of the periodic function f star. You can insist that. And of course, you will, by theorem 11.1.2, you will have trigonometric Fourier series extension. Okay? For f of x in this one period. Okay? And we have two other alternative choices. One is that we extend f, right, to an even periodic function. So what is that? Well, is one even periodic extension. Right. So let me draw a picture for you. Now, we have so suppose we use this version that the function f function has value say about 1/2 at point L. Yeah. And we will regard that we want to construct an even periodic function. How can we construct? Well, we just construct an image of this part through the mirror. The mirror here is the y-axis, right? So we construct that here. Maybe I use different color. The chart is different color here. All right. So they have the same point, and okay. So this is just the image, right? The image of that. Okay, and so this is one period. So this periodic function, the periodic function becomes a period with a period which is 2L instead of L there. Okay, and so so we will have so we have here and there. Okay. Etc. All right. So now we have. So sorry. This is my extension. Okay. So we have an even periodic function here. Right. So now this one is an even periodic function. An even periodic function. Okay. And f of x here is just in a half range, in half of the period. So that's why we call half range extension, right? We now have that. Okay. Right. So so the definition, the formal definition here is that we define okay, and zero. Okay, so we define that. All right. So by this definition, and also right. Okay. So but we define this periodic function within one period of 2L, right? And then we repeat in the other period. So this is the definition of the function. Okay, and so that this periodic function, because this periodic function satisfies the condition required in theorem 11.1.2, so we have that okay, so that is okay, okay, so so f of x is equal to this, and this series is called Fourier cosine series. Because it consists of cosine function. Okay, so it's called Fourier cosine series. So this. Thus, we have f of x equal to the same and the an, I have to write down what is the an. Okay, so I have to say a0 equal to 1 over L to dx, and the an equal to okay. Remember, when we have an even periodic function, the trigonometric Fourier series becomes to the Fourier cosine series. We mentioned that last Thursday, right? And we know how to compute Az and An just by using the half period, right? so you can compare the expression we mentioned the last Thursday. So that's so we have that. Okay, so this representation you can see. Actually, I'm sorry. Actually, it should be this way. But I think I have to write carefully. This is equal to, because in this half period, this periodic function is equal to the original function. Okay, and okay, the same. Okay, in this expression here. So that is the situation, and then that is we have. So finally, we have f of x equal to in 0L, where f is continuous. Okay. So now we are able to represent the original function in this interval, right? By using a trigonometric Fourier cosine series. Maybe I like. Okay, so we have such function, and this is true for every for all points. X in here, maybe X in R, right? So this is X in the finite interval from 0 to L. All right, so this is the case one when we construct an even periodic function. Let's do add extension. All right, so now we use the same example. So we have that. So this is our f of x. And now we would like to construct an arbitrary function. So for arbitrary function, we have to find the symmetry of this branch through the origin. Okay, so through origin, so we should have here and here. Right? Now, the value at L and minus L, in this case, are different. Okay, are different. So in the construction, so what we have arbitration. So for my arbitration is here, that we go over to here. Okay, go over here, and then I select. So my decision is that here, okay, and right. So we have f of x. So you can observe that here. The f odd x star hello is not equal to hello. It's possible. But they may be distinct at one single point. It's possible. Okay? It's not in this case. But that's fine. They are different at one point. Okay. So the definition, the proper definition. So we define just like here, f star r is defined to be f of x is then double here, and minus f of minus x okay, so we define and right, so can be arbitrarily one. And finally, f0 star x plus 2l equal to f okay? Sorry. So it's possible that the fr, the star, is different from f of x at the point 0 or at point L. It's possible. But this is situation, they are different only at L. But it's possible that they are different at the point 0 here. Okay? But that's fine. With only 2 points, they are possibly different. Okay. So this is the proper definition of the periodic extension. Okay, and so now the f0 star of x can be written by so this is a trigonometric Fourier sine series. Okay, so it's a sine series. And for its all points x in R, where f0 star is continuous. Okay, so this is an equality for all point x in R in the whole range, where the other periodic extension is continuous. And Bn, okay, compute it. F of star x sine. Okay, so by the periodic extension over half period, and in this half period they are almost equal except 2 boundary points. So every point has length 0, so we can replace this the periodic extension to the original function. So we have that. Okay, so we can represent that, and because they are equal, right, in this open interval, so, and then thus we have f of x is equal to summation from 1 to infinity bn sine and pi x L. It's all points x e 0 and L. So now I just restrict all set to the open interval 0 and L. Okay, so at all points where f is continuous. Okay, so now we have a satisfactory theory about representing a function f defined in a finite interval from 0 to L by a Fourier series cosine, a trigonometric Fourier cosine series, or a trigonometric Fourier sine series. Okay, so later on when we apply this technique to solve the partial differential equations, we basically will use a half-range expansion, because these two expansions are simpler than the original one. So do you have any questions? Alright, so if no, now so I will go to section number 3. We'll talk about an application to so-called forced oscillation. So it's an application of Fourier series expansion. Okay, so our purpose is to apply the theory of Fourier theories to solve differential equations. Okay, and but we need something. Okay, and to apply the theory of Fourier theories to the solution of differential equations. We need to make sure the validity of the interchange of to study the current flow through this simple circuit. So we know that that L times the dI dt plus Ri plus 1 over c, the integration t, for example, maybe there's something it is equal to d of t. Okay? Because the voltage, okay, over the inductance proportional to the derivative of the current flow rate. And the proportional constant is just the inductance L. Okay. And this is the voltage drop across the resistor. Okay. And so it's proportional to the current, so the constant is just the resistance. And this is for capacitor. Now you have to integrate because it depends on the charge, right? This is the total charge to the capacitor divided by the capacitance. Okay. So this is the voltage drop across the capacitor. And sum together is equal to the force. The voltage is called, we know it is the electrical force. Right? So we have this, we call the differential integral equation. And we can make the differential integral equation into differential equation by what? By differentiation again, right? So that this comes to L. So let me just say that L of the prime means the second derivative plus I prime plus 1 over C I is equal to E prime T. Okay? So now this is a second order differential, ordinary differential equation with constant coefficient. Suppose all these RLC are constant. Okay? It is possible, depends on time or even on other parameters, but for our study, I just assume that they are constant. Okay, so we have for this one, so this is a second order. Okay, second order ODE, ordinary differential equations. And assume that you have already taken the course on OED last semester. Okay, I assume that. And so now I can just write down something. All right? Okay, so the general solution, let me just write down something you are familiar with in the OD course. All right, so the general solution of the OD, okay, so let me say this is 11.3.1, okay, 11.3.1. Right, is the sum of a homogeneous solution and a particular solution. Okay, so we have homogeneous solution. Homogeneous solution means that if we have no external force, so the external force is 0, then you have homogeneous solutions. In second theorem, that means that without any external force, it's possible that the inductor or the capacitor stores some energy inside it. Okay, so you have inertial energy in these two components. You know, resistor cannot store energy, but it's possible to store energy for this component. Alright, so any homogeneous solution related to any inertial energy there. Okay, so they have some signals there. So homogeneous solution corresponding to the inertial energy inside the circuit. Particular solution corresponding to the external force. Okay, external force. All right. So now things, because all LC, they are all positive quantities. So the ratio actually is positive. Now, so this ODE, okay, govern a damped system. So this is a damped system. A damped system is that without external force, even though you have initial energy, energy will go to 0. Why? Because you have resistance here, right? So the unit will turn the energy, the electrical energy, into what? Into thermal energy only, right? So dissipation to the airs and vanish. Okay, so it's called the damped system. And we can see that, so this can be seen from the homogeneous solution. Okay, so let me write down the homogeneous solution for you. Your reference here. Of course, you can solve it because this is a very simple second order linear differential equation with constant coefficients. Okay, so it's quite easy to solve it. But let me write down. Oh, okay. All right. Actually, I run out of my time, so let me. So we have three cases to write down. C1 exponential r squared minus 4L divided by C divided by 2L T plus C2 E minus T. If the discriminant divided by C is greater than 0, okay? This is the first case. Alright, if this is positive. But if the discriminant is 0, then you have C1 plus C2T. Is 0, okay? And finally, if this discriminant is negative, then you will have cosine sine function, cosine. And so, T C2 sine Alright, so you have that. And you can see that as t goes infinity, this has exponential decay, right? Alright, so it goes to 0, the finished, because this decay much faster than the linear term. And even though you have positive exponent, but this exponent, the constant is less than this one. Okay, so when you multiply together, you have a negative exponent term. Okay, and so it decays exponentially. So that's okay. So that means that without the external force Et from the current, okay, the current will diminish to 0 exponentially fast. Okay, so that is right. So now, so thus we know as t goes infinity, the solution of the ODE, okay, approach the so-called steady state solution, okay, which should be a particular solution. Of the ODE. Okay, So we will focus on the steady state solution. Basically, in circuit theory, we usually study the steady state solution of the circuit. Okay, so that is the situation. So we will ignore the homogeneous solution because it is transient and goes to zero exponentially fast. All right? And so we will only study the steady state solutions. Okay, so I run out of my time and I will continue the topics on Thursday.